Cool, all right. Yeah, thanks for coming. I'm Dirk. I wrote a package to model mixed integer linear programs. Those are optimization problems, or a special class of optimization problems, and this package makes it, in my opinion, sometimes easier to model these kinds of problems in R. So maybe a first question, who of you have heard of linear programming before or used it? Okay, cool. So like 3/4. Okay, so this is the outline of the talk, so I'll quickly introduce mixed integer linear programming really quick, then how you would usually do it in R using matrices and vectors, and then I'll show how the ompr package does it, and in the end I'll close the talk with some conclusions and future plans for development. So mixed integer linear program, I just start with a small example I took from Wikipedia, so you can think of it as an optimization problem. As I said, it has roughly 3 components. An objective function that tells you what you want to optimize, maximize or minimize. A set of constraints that define your search space where your valid solution is in. And then some conditions on variables. So in this case, this is a small example. On the left-hand side, it's a program with 3 variables, x and y. We want to maximize y, so find the maximum value of that variable y. And we have 3 constraints. Minus x plus y smaller equal to 1, 3x plus 2y smaller equal to 12, and 2x plus 3y is smaller equal to 12. So these 3 constraints, they constrain our search space where we can find or try to find the optimal solution. And it's pictured on the right, and since it's only 2 variables, we can actually solve this problem graphically. So the constraints that define that search space are those blue lines, and if you just increase y until you hit the top vertex, that's the optimal solution. But there's another constraint in this case, and that is x and y need to be integers. So they cannot have any fractional values. And that makes the problem way harder. And in this case, it reduces the search space a bit more, and only those red dots are now valid solutions. So in this case, the optimal solution would be y equals 2, because that's the most integer value you can achieve. So here we have 2 optimal values, y equals 2 and x equals 1, or x equals 2. And you can formulate that a bit more generally in terms of matrices and vectors, as I said. And that's the natural interface towards these kind of problems. So you maximize a linear objective function described by a vector C and a set of linear constraints that you can describe as a matrix A and a right-hand side vector B. And then again some conditions on the variable like bounds and if they should be integers or binary variables or continuous. Applicability, so it turns out these kinds of, or there are a lot of real-world and not so real-world problems that you can formulate as mixed integer linear programs, such as designing the best route for pickup and delivery service, or finding the optimal rosters of doctors and nurses in a hospital, trying to build a timetable schedule, and really a lot of interesting problems can be formulated as these models. And since there's so much applicability and it's such a nice interface, people have started developing specialized solvers that can take that problem, solve it to optimality, and you get an optimality proof sometimes, and then you can further process that result. And in R, there are a lot of interface packages to these solvers, both for open source on the left-hand side, like GLPK, the GNU Linear Programming Kit, or LPsolve, Symfony, and numerous others. And there's also a lot of commercial software around, and if you're affiliated with an academic institution, you can usually use it for free, which is quite nice for those of you who are affiliated with an academic institution. I'm not anymore. But those are really, really good and sometimes way better than the open source alternatives. And there's also a task beyond CRAN. So this is mixed integer linear programming. Now, how would you model that in R? So one natural approach to use that matrix and vector interface, and that's perfectly fine. It's really a natural interface for that problem. It's really efficient. So this is an example from the package ROI. It's a great package. They came up with a unified interface that lets you formulate your problem once and then pass it to different solvers. So you don't have to learn the API of GLPK or Gurobi or Cplex. And the way you would do it here, so we see our example from before, you would describe it, as I said, as 3 components, a top-level vector CV, 0, 1, so 0 times x plus 1 times y, a matrix A with 3 rows, 2 columns, one column for each variable and 1 row for each constraint, so minus 1, 1, 3, 2, 2, 3, and then a right-hand side vector B, so 1, 12, 12. And you would put that into the optimization program and add some more information like the direction of the constraints here, so they're all smaller or equal to. It's a maximization problem. You would also set 2 bounds for the 2 variables you have. They need to be smaller, greater or equal to 0, and those 2 variables should both be integers. And you can do this, pass it to the GNU linear programming kit in this case, and you get an objective function already identified before. The optimal solution is 2, and you can also get the solution out of there. It's 2, 2. So this is the matrix-oriented interface. But what about more complex problems? What if you have something like this? Or if you scribble around on your notebook in front of you, write your equations down. If you want to simultaneously test it in R, you always also have to write code that constructs a matrix. And at least for me, that's sometimes difficult. And this is where the ompr package comes in. So this problem from before is formulated as this. So similar to a deployer statement, you would start with an empty mixed integer programming model. You would add a variable x, type integer, lower bound 0, add a variable y, set the objective function, it's simply y, maximize it, and then you would add the constraints. And you can just simply write it down as just normal equations, and the package will take this expression, multiply it around, put the constants to right inside, and does all that stuff for you. And looking at this, it's pretty much clear what you wanted to do. Looking at code that constructs a giant matrix, it's sometimes not so clear what you had in mind. So that abstracts away all the matrix creating code. And here, similar to ROI, you can also formulate this model, pass it to solvers. And I wrote a package that can take ompr solvers and put it to ROI, so you can use all the solvers that are available there. In this case, we solve it again with GLPK. Optimal solution is 2. You can also get the solutions out of the model with a function called getSolution. Yeah, so here's a more complex problem where it gets more, I think, clear why this is useful. This is the so-called knapsack problem. So I have a bag with me and n items. I want to put in as many of these n items in my bag as possible. Each item has a value, and each item also has a weight. And my bag has a capacity on that weight. So I can only take a subset with me. And this is the classic knapsack problem. You can formulate that as an integer program. And the way you would do it, you would create a variable xi for each item. That's 1 if you take it with you, and 0 if you don't. And you maximize the weighted sum of these items with the values subject to the total weight, and that needs to be smaller or equal to your capacity. And you can naturally express that in ompr using indexed variables, and you can also use parameters from your environment. So here I create an index variable from 1 to n type binary, and I add a sum expression, vi times xi for all 1 to n, and a second constraint as well. So it gets really quite natural how you can formulate these also kind of larger problems. And if you have index problems, we can solve it, we get a solution, and for index variables, the solution is exported as a data frame. So you can formulate your model, solve it, and just pipe it right to dplyr and, I don't know, plot it or do whatever you like with it. So here you get everything as a data frame. And I think the real nice thing about it is that it can handle quite complex expressions. So this is a constraint from a traveling salesman problem, from a specific formulation, and you can just simply write it down in R and the package will take care of all the parsing and multiplication and constructing the matrix, and you don't have to do this by yourself. So, yeah. And this also, yeah, already leads me to the conclusion of future outlook. So this package was inspired by me reading the book on advanced R by Hartley Wickham and the section on non-standard evaluation, because it uses that quite a lot and quite heavily. And I'm now almost done. It's on CRAN. The API is in such a way that I like it, and I think it's quite nice. So that's what I focus on first. And now all the rest comes after, like increasing performance and stuff. So some side effects while developing it, I needed to test the package with all different kinds of optimization problems. So and whenever I did this, I wrote an article about how you can model that in R with ompr. So here are 4 examples. On the top left, there's the famous 4 coloring problem. So coloring a map with as few colors as possible, and no 2 adjacent counties or elements can share the same color. On the right-hand side, there's an article about a traveling salesman problem, visiting a set of nodes and then returning home in the most cost-efficient way. On the bottom left, there's an article about the warehouse location problem. So if you are a large logistic company or an NGO and you want to distribute goods and you have a set of places where you could open up a logistic hub and then serve your customers, you can reduce that to that warehouse location problem. And then you can also do interactive stuff. So I wrote a Shiny app to solve Sudokus. It's not really an optimization problem, but still you can solve Sudokus with that. For those of you who might need it, it's out there. So it's almost the last slide now. There are 2 tracks I want to follow. There's the ompr side. So I'm almost done with sparse matrices, so it gets more memory efficient. That will definitely come into the next CRAN version. I'm still not fully sure what matrix package I'll use and what encoding for the sparse matrices, but that's almost done. Performance optimization is a quite important thing because that adds a quite huge layer of abstraction and it just costs computational speed. So that needs to be reduced further, but I have some ideas to do that. Since it uses non-standard evaluation quite heavily, I definitely have to look into RLang and tidy eval and things that have been presented here as well. Of course, currently it only works for linear models, but you could also extend it to quadratic constraints and quadratic functions as well. And I'm thinking of different backends, simply like dplyr. So, for example, you could have a backend that just instead of evaluating your model, it just sends it to your favorite cloud solving solution, solves it there, gets it back, or compiles it to an efficient C++ function, then solves it. So those are some ideas for the future. And then on the mixed interlinear programming side with R, CBC is almost done. That's kind of one of the most efficient and best open source solvers. So that's workable with the help of Jeroen Holmes. He helped me a bit with it. So that will hit CRAN soon, I hope. And then 2 things that are really important for solving these kinds of problems are initial starting solutions. So sometimes you can supply a known solution to the solving process, and that speeds up a lot. Currently, not really possible, except for like specific API packages, and then lazy constraints and callbacks. So I recently had to implement a model in Julia because there's just no way to use callbacks in R, and callbacks are sometimes a vital point to change the solution process of these solvers. So sometimes you don't want to, for example, create all exponentially many constraints, but only add constraints if they are violated. And using that, you can solve larger models like traveling salesman problems. That's it. Thanks a lot for bearing with me. The package is out there. It's on CRAN. It has a couple of batches. I'm happy to hear any feedback. And there are, as I said, a bunch of articles and tutorials out there as well. Thanks.
Hello. Hey. It's a very nice, congratulations, it's a very nice package. I will be probably a user. I use LP solve to write the problems, but usually I write some wrappers to call CVC. You call CVC directly, or like the standalone, or is like calling the libraries?
Yeah, so there's a package called rcbc on GitHub. It calls the C++ interface currently. I think using the binary, I don't know if that's the ideal approach, but that's the interface, and it works.
No, it's not the, but you know, the standalone binary of CVC is really efficient.
Yeah. So that's there. If you search for rcbc, you'll find it. But it's currently just on GitHub. It needs some final fixes, but it definitely works on Linux and Windows, and I think even Windows. Yeah, but I don't have Windows, so but it should work.
Okay, thank you.
We still have time for
Thank you. Nice work. I like it a lot. I will use it, I think. Just two very specific questions, so if they are too specific, just ignore them. One of them is sometimes you need to give some extra parameters to the solver, some kind of epsilon for, you know it. So I didn't see this quickly how your package will support that. That's one specific question. The other one is, in my programs, I often have strict inequalities, and most solvers don't do strict inequalities, so I have to do all kinds of tweaking to resemble them. Any ideas about that?
Okay, so the first question about the parameters to the solvers. So ompr in itself is just a package to model stuff, and there's another package called ompr. So that's essentially just a function mapping it to a solution. And ompr, for example, passes all exposed parameters to the specific solver. So you can say in CBC time limit equals 60 seconds. And then in terms of equalities, I mean, some solvers offer dedicated support for it. But that, I don't know if ROI supports strict equalities. I don't know. I guess, and then you have to use the usual techniques, like, I don't know, subtract an epsilon or something.
Okay, thank you, Dirk.